So it works. Quantum mechanics works. Wow. All that weirdness, and it does make good predictions. Okay, so now let me tell you a little more about these lines. These are very important. Those lines of color, they're actually 4 different lines. But on this, because of, look, it's NMSU, and, it's been around a while. Those blue lines kind of get scrunched together in one big line. But it'd actually be 4 different lines that you can see. So let me ask you this question. Can the electron go from 6 to 1? Is there anything that says it can't go from 6 all the way back down to the ground state? Have I said anything about that? No. So why didn't I talk about it here? We should be able to see that transition too, right? From 6 to 1? Right? I mean, that should happen because the electrons want to go to the ground state. Why didn't I talk about it? Maybe there is something wrong with quantum mechanics after all. What do you guys think? Why do you think I didn't talk about it 6 to 1?
Maybe because it's
Negative?
negative.
Be a fission reaction?
No. Well, think about it. What is a 6 to 2? What kind of light is produced from a 6 to 2 transition?
Oh, I get it, because we won't be able to see.
There you go, right? Because the 6 to 2 transition is right at that 410 mark, right?
Oh, yeah.
Anything less than 400 we can't see, it's invisible. So this does happen, the 6 to 1, but the light that it comes out is ultraviolet. It's in the ultraviolet spectrum. Does that kind of make sense? It's too small a frequency to see. So we only looked at what are called the visible lines, and the name, and please write this down, because you'll probably need to know it. The name for the visible lines that we can see from hydrogen discharge, that name is known as the Balmer Series. The Balmer Series. They were actually discovered by Balmer, who was a school teacher. I forget, it was the 17 or 1800s. It was a while ago. He was a school teacher, and he discovered these lines. And when we look at these lines, here's the interesting thing about these lines. Every atom has its own unique set of discharge lines. Every atom. Because the electrons are in slightly different energy levels and slightly different configurations. So every single atom, if I were to do this, excite the electrons in those atoms, every single atom would give off spectrum. And the spectrum would be different from atom to atom. Hydrogen would be different from helium. Helium would be different from neon, and so on and so forth. Every atom has its own unique set of spectral lines. And the spectral lines are more or less a fingerprint for an element. And in medicine, that's really handy because maybe there's some substance that I'm testing. I don't know what it is. I could excite the electrons in that substance, and I could break that light up, and that light would tell me something about it, could help me identify that substance. That's called spectroscopy. We also use this in space, as somebody who tried to steal my thunder. We can look at distant stars, or we can even look at our own star, or even a planet. And we can take that light, put it through a spectrum, and that light will break up into its emission lines, and then what can we say about it? Oh, I know that this element must be in that planet. And the brighter the lines, the more of that element, right? So what do you suppose we see really bright when we look at our sun? Or any star, for that matter. What lines are really, really bright when we break that light up into its spectrum? What do you suppose we see a lot of? What's the sun made of? Hydrogen. How do you think we just know? Did we go to the sun? Have we ever been to the sun and taken a sample of the sun and said, yep, that's hydrogen? No, we took the light from the sun and it made a similar series of lines as this hydrogen over here, and we went, wow, okay. And then from that we go, okay, so what the sun must do is it must fuse hydrogen into helium because we see a little bit of helium there. And I can do that with objects in the night sky and take that light, break it up. How do you think we knew that there was iron and other minerals on Mars? How do you think we knew that there was carbon dioxide on Venus? Or helium and hydrogen in the gas giants, Jupiter and Saturn? When we never even went there. Well, we've been there now, but how do we find that out? Well, we looked at the light, and we looked at how they emitted, what light they emitted. And the interesting thing is every element absorbs certain light at certain wavelengths, right? If it emits, then it stands to reason that it must absorb at certain wavelengths as well. And that gives things the colors, right? For example, I look at this. This is an orange color, right? So this is absorbing all the other colors, but it's reflecting what? Or, yeah, yellow, orange, kind of this bile green looking stuff, right? Yeah, right? It's absorbing the other colors, and it's reflecting, and every material, is different, blue, and obviously white is pretty much every color, or none, known, and black, of course, is going to be, lots of colors. And, so we can also use the absorption of light in medicine, and we use it every day in respiratory therapy, right? You guys have started clinicals. What do you do to your patients every day? How do you assess them? What do you assess? Pulse oximeter, right? You throw their finger in a pulse oximeter, and we know that hemoglobin, deoxygenated hemoglobin, absorbs different wavelengths of light, and oxygenated hemoglobin absorbs different wavelengths of light, right? And that's how a pulse oximeter works. It detects how much of a certain type of light am I absorbing. If I'm absorbing more of that, it's obviously it's red light. If I'm absorbing more of that light, then there's more oxygen there. That's how pulse oximeters work. They work on the same principle. They work more on absorption instead of emission, but it's the same principle. It's all electrons either absorbing light or emitting light. And they emit in very discrete or very well-defined levels of energy, depending on the atom we're talking about. Okay? So what I would do is I definitely look up Balmer Series on the internet and actually take a look at what, if you used a really sensitive and specific instrument, you could actually, and you'd actually see those 4 distinct lines. The best we can get with the equipment here is the 2 lines. These tubes obviously have been used and used and used, and you get some contamination, some light and whatnot. But anyway, I can still give you a pretty good idea of what's going on. Now what I want to do, just to prove to you that every atom has its own distinct set of lines, is why not just throw another atom in there and see what happens? What do you guys think? So let's do that. We'll do it with our little little rainbow glasses here. And instead of hydrogen, let's go ahead and do neon. Neon has a lot of electrons, right? What is it, 10 electrons or something like that? Forget this noble gas. Is it 10, I think? 8, yeah, octets, let's do, yeah, I think it's 10. So let's go ahead and do neon, and we'll do the same thing with neon here. Take a look at it through the rainbow glasses and see. Ooh! Wow. So the red lines, you can see there's a lot of red and yellow, and not a whole lot of blue. Can you guys see that?
Green.
Yeah, it's some green even. That's very different from the hydrogen we saw, isn't it? So you can tell that every element has a distinct set of lines. And what I'll do is I'll set this up. Okay, and then you guys can come through and take a look. And you'll see that the lines, the spectral lines, are so different on this one. Lots of red and some yellows in there.